Okay, so in chapter 7, so we're going to move on to chapter 7. So using our propensity score approach. So this is very popular technique actually. So let's introduce. So this is the estimating function, estimating equation. And then if we observe, right, if we observe Z, then we'll use this. This is kind of a measured moment estimation or estimating function. And then, so parameter theta null, true parameter theta null is the solution to this integral equation. And theta hat, this is from theta hat, right? So you have an estimator, and then this estimator will converge to theta null if the expectation of the u function at theta null is equal to 0. And question is, we have a missing data in Y. Then we have two approaches. One is the prediction of model approach, which is a predict, right? So this is Y. So this is sometimes we call it outcome model approach, outcome regression model, or outcome model approach. And another approach, so that's actually prediction approach is essentially imputation approach, and that's been discussed so far, right? And now we have a totally different approach, which is originally motivated from survey sampling. So in survey sampling, we treat, so delta I is the sampling indicator, and then you use the probability to draw or distribution free, right? Design based inference. So that's kind of a totally different framework, and that was not really, that's very separate topic for a while, but in early 1990, so in 1990s, Robbins basically uses this technique to develop the causal inference, and that opens up a lot of follow-up papers and research. And so nowadays, this is very hot area of research in even these days. So anyway, so let's so this is the main focus of the chapter 7. So which I plan to cover about 2 weeks, from this week and next week. So yeah. So that's a good question. So we in survey sampling, actually this is known. Okay, so the selection property is known because it's under the control of design. I mean the sampling designer. And missing data, this is unknown, right? So we need to model. So that's the main difference. Okay. So complex case model, complex case method is just use the, right? Use the observed data only and hope that this is okay. And now the question is, under what conditions this is valid? Turns out that if delta, the covariance between delta and u is 0, then CC estimator is unbiased. How to show that? Well, so we should to show that expectation of the I equal to 1 to n delta I u theta null ci equal to 0, right? So this, so we want to show that this one implies unbiasedness, and unbiasedness is actually nothing but showing this. So what we really want to show is this guy implies this guy. Okay. And now, what is this? Basically, this is a we are talking about IID situation. So this is actually n times expectation of two random variables, U and delta times U set, right? And so this is IID, so we can move n outside. Excuse me. And then delta times U zeta null, right? Evaluated at zeta null. So U is just a function of Z, and then the value is evaluated as zeta null, right? So then this one is equal to covariance of delta and U zeta null plus expectation of delta times expectation of U zeta null. And then by definition, this is zero, right? The definition of zeta null is the one that makes this one zero. So that means this product, right? Expectation of the two product is equal to the covariance. So that means because we already assume that delta and U has a covariance zero, right? So we assume that this is zero. That means we have this equal to zero. Okay. So bottom line is, if delta is completely independent of Z, then CC analysis is okay, right? So that actually is a missing complete at random, right? So MCAR, missing complete at random, it means this one, right? So which kind of confirms our understanding on missing complete random. But as we all know that CC analysis, I mean MCAR may not be true, right? So and also well, we are talking about the solution. So for example, suppose theta is expectation, could be so then yeah, so how theta is defined through what? Through y minus theta x. Okay, suppose so so that means theta null right? Theta null satisfies expectation of U theta null, where U is the y minus theta x, right? So this is, for example, so this one, so estimating function is unbiased, right? Estimation function is unbiased to zero, but the solution to the estimating equation, which is the theta hat, right? Theta hat. So the solution to the estimated function will be y bar divided by x bar. Right? You have a sample. So this is not exactly unbiased to this one, because the numerator is unbiased to expectation y, denominator is unbiased. But this is not really unbiased to this one because of the nonlinear, right? So point is that because the estimated function could be a nonlinear equation, so you can get you cannot really guarantee that solution is unbiased, but can be approximately unbiased. So okay, and CC method does not make use of the observed information, so this is not efficient. So we are basically throw away partial observation, so that's not really good, right? So we want to do something better. And the starting point is to use weight using the inverse of the known propensity. So suppose this is known. Okay, suppose this is known, then we can use the probability is known, that you can use the inverse as the weight and solve the weighted estimating equation. So this is actually, as I said, this is has a survey sampling, you know, motivation that is called Hurwitz-Thompson. This kind of method is called Hurwitz-Thompson estimation. And actually, Hurwitz-Thompson, they are one is I think Hurwitz is a professor at Iowa State University, and Thompson was a master student in Iowa State University's Department of Statistics at that time, the 1951 something. So, but this paper is one of the 10 highly cited paper in the history of the statistics. I mean, right? This is really a breakthrough at the time. Okay. Well, okay, why this works? Well, so we need to show, so unbiased, how asymptotically unbiased. So then we want to show that this weighted, we want to show that this guy and delta I, 1 over pi I, u zeta null ci is equal to 0. We should show. So we want to show this. And the left side is you can do we want to do something like this. So this is the expectation where the random variable is x and pi. Pi is also random because it's a function of z. So the function of so delta pi z, they are all random. So there's too much, right? So then we want to do one by one. So let's conditional on z. So if you conditional on z, this is fixed, right? Fixed. This is fixed. Delta. So pi is also fixed. The only thing random is delta. Okay. So then you can basically exchange the old, right? Exchange everything. So you have something like delta I given ci and 1 over pi I, u zeta 0 and zi, and then you take the expectation. So because you have a expectation of the expectation, right? So you expectation of conditional expectation, and then condition is this guy is cancels to with pi I if there's actually one important condition. If these pi i's are all positive, if the pi i's are actually zero sum for some I, then this is not really true, right? So we under this condition, known and positive, we get cancellation, and then expectation comes inside, right, to u, and which is 0. So then you can get 0. Okay. So another way, if you remember the lemma 4.1, something like that. So roughly speaking, set ahead. So this is about the solution to property of the solution to estimating equation. So u zeta null. Oops, not really. Expectation. and then minus, minus inverse U set tunnel. So this is, if you remember this lemma, so this is has zero expectation if this one has zero, but approximately. So we have this one. And secondly, so the variance, let's talk about the variance. So what's the, how to compute the variance of this solution? Well, this is estimating, right? This is essentially kind of estimating equation. So we should expect that the solution, the asymptotic variance should follow the sandwich formula, right? So that we have a sandwich formula, and then the center part is actually the variance of the estimating function, right? You have, and then the gamma, the sandwich part is just the partial derivative. So the partial derivative should be unchanged, and the variance part is changed, and the variance part you can see. So let's look at this carefully. So what is this? Well, see, this is, so we are trying to do the same thing, but so let's let's use 1/n to make it life easy. But so U set tunnel, UI set tunnel. So we use this kind of notation. So we are interested in evaluating the variance of the weighted UI, right? And then because we use the conditional expectation, right? So we kind of do the law of the conditional expectation, and so we want to do the same thing here. So we want to do the variance of the conditional expectation of the conditional variance of the conditional expectation plus expectation of the conditional variance. Okay. And then inside, the only thing random is delta, right? Inside is delta is random. And then so then the expectation here, you just have a delta expectation, which is pi, so cancels, so that you have this one. By the way, what is this one? This one is just the sample mean, right? Type, right? So then this is I equal to 1 to n ui set tunnel. Okay. So that's the first one. And then second part, you want to, so what is the random? Is a delta, right? So you want to do compute the conditional variance of this guy with respect to delta. And then which is basically delta, what is the variance of delta? Pi I times pi 1 minus pi I, right? Because it's Bernoulli. So pi I 1 minus pi I divided by pi I squared, which is this guy. Okay, and then ui and then ui prime, right? So that this is which is this. So that basically have the prove the first part, and then second part, the usual trick is that you can write it as a 1 over. So what is the variance? Variance is what is variance? Variance is you can write it as a 1 over n minus 1 summation I equal to 1 to n ui minus u bar square. Okay. So the usual trick is we want to achieve some kind of cancellation so that we can write it as an expectation. So one way to do that is this is one. This is just the sample mean, right? So variance sample mean, which is the 1 over n times s squared expectation. So then you have something here, and then you have a here, and then do some simplification. Then basically here, so let's write it as a 1 over n squared summation into 1 over n ui squared minus so if you do so then it's kind of u bar square. Yeah, this is a little bit messy algebra, but you can basically see that you have a square minus 2 times the cross product and then minus u bar, and then you have some cancellation. Then end of the day you get something. So our point is that this guy. So this guy cancels with this. You have a second term here, second term here, cancels with the first term. And then what is left is the first term here, right? This term, which is this term, minus this term here. And then if you and then this guy is non-negative. I mean, this is some positive term, but this guy converts to 0 because the expectation. So this is sample mean of square, right? And sample mean converts to 0. I mean, because the population mean is 0. So asymptotically, this is negligible. So then the formula, end of the day, the formula is kind of simply quite simple, right? So basically, end of the day, your variance formula is 1 over n times the Propensity estimator of the square, right? So you see, so you have a one, you have a 1 over n. 1 over n comes because you have a variance, and then basically this guy. Well, not, it's not true. That's not really Horby-Thompson estimator. Actually, you have a, sorry, this is, actually, if you use Horby-Thompson, this is Wi square, actually, Wi square. So delta I cancels with pi I, right? So this guy is actually, is if you think 1 to n is population, this is actually over the population. But anyway, the form itself is my point is that the final variance is actually relatively simple. The formula.
Okay. So
yeah.
Other conditions independence between.
Yeah, right. I should have told. Right. This one is a condition that so you don't really have to talk about this, but the response. So in the missing data context, we assume that response mechanism is independent of itself. So whether I respond or not is independent of whether you respond or not, right? It's a kind of an assumption, typical assumption we make.
But here you do not need to assume the independence between Z and the delta.
No, right. So actually Z and delta could be correlated. So there's no problem. What I assume is the independence of between delta. I mean, different for different delta.
But when you calculate the conditional variance, right? So
here, right.
Right, you give Z to calculate the conditional variance of the delta, right? So that has to be use the independence of delta given Z. Otherwise,
I see. So you are saying that this is actually conditionally independent. You mean this one?
Right.
Yeah.
Right, so that is to deal with the covariance, right?
Right.
Dealing with the variance.
That's right.
Variance of delta in Z.
That's right. Yeah.
So they assume the delta and Z are independent.
Yeah. So actually the whole see delta I Ci as a vector. IID. So we are so this is actually better way to understand. Okay. So we allow delta and Z can be correlated, but across different I, right? They should be independent. Yeah, that's a good point. Okay. And then, yeah, so then because once we have a sandwich formula, we can easily compute the variance estimator for each component of the variance. So we can move on. So this is an example. So suppose we are interested in population mean of Y and using propensity weight WI, I mean the pi I. Then the equation you want to solve is this one. Delta I divided by pi I and yi minus zeta equal to 0. Right? So you want to solve this. So if you solve this for zeta, you will get this. So then when you compute the variance, basically this is a ratio type estimator. You have a randomness in both numerator and denominator. So the usually requires a Taylor expansion, but this sandwich formula already takes care of that linearization in some sense. So basically you so what is so if you tau, what is tau? Tau is the partial derivative, right? So in the sandwich formula, the tau here is equal to -1. Right? Your u function, right, is y minus zeta. So tau is -1. Okay. So you in the variance formula, remember tau inverse variance of u hat, right? W and variance tau inverse prime. And then now this tau is 1. So you don't have to worry about the red part, and you have only to worry about this one, which is actually using the formula here. This which is essentially this one. Right. So that is the variance formula, and then you can use the sample to estimate. So you don't observe yi throughout, right? So you need to use the Horobi-Thompson idea again to estimate this guy. Okay, so that's basically the idea. So the class in the class next Thursday class will mainly cover if we have a model. Okay, so chapter 7.3, which is with Thursday class, and fee is unknown. We'll talk about all these issues because we don't. So the theory here is pi is unknown, right? Everything we assume pi as known. In that case, everything is clear and easy. But if we don't know pi I, but we do have a model, and we have an unknown parameter in the model, then we need to first estimate the parameter first, and then use that to adjust, right? To use the weight, right? So that is the actually more realistic situation with the missing data. So that is going to be covered in the next class. But for now, we'll just focus on some basic theory with associated with pi I, using pi I. So one interesting point is this. So suppose we have a axis decomposing x1 and x2. Okay. And we see a random actually falls under x1. So that means the condition about y delta equal 1 given x1 and y is independent of y. Okay. Then the problem becomes a little bit interesting, because you can think of two different propensity score models. So conditional probability of delta. So first one is using x1 only. Okay. The other one is using x1 and x2. Okay. So I'm going to use tilde to emphasize that it's only using x1 and pi as the original one. Okay. So that's why we have a full model versus reduced model. Sorry. So full model means we have using x1 and x2, right? x1 and x2. And reduced model means using x1 only. Okay. And then in this situation, if you are interested in estimating the population mean of y, we have two choices of the WCC estimator. One is using pi xi, original one. The other one is using pi tilde as the inverse weight, right? So first of all, both of them are unbiased. So I'm going to show you this. So first, W1 theta null is 0. So is this 0 equal to 0? Yes, because we already see that, right? Because the property of delta equal to 1, given x and y is equal, right? So then we have cancellation. And then secondly is W hat you had 2 theta 2 is 0. And the answer is also yes. Because if you take the conditional expectation, even x1 and y, right? Even x1 and y, the delta is using this property is equal to pi tilde. So you have cancellation still. Okay. So both of them works. I mean work very well. So then natural question is, which one is better in terms of variance?
Well, you do not have BC and the random, right? You only have BC and the random given x1.
You mean the
For equation 3.
So yeah, that's a good point. So I think we should. So for this to be, that's a very good question. So for this to be, you mean we should also assume this one? Right? Otherwise, right. So yeah, right. You are right. So under this one, we have this property,
Right.
and under this one, we have this property.
Right.
Okay. So basically, suppose delta is completely independent, right? I mean, in that case, this should be okay. So now the question is, which one is better? And turns out that theta 2 is better in terms of variance. What is theta 2? Theta 2. Theta 2 is the one that uses the smaller covariance. So reduce the model. So let's try to understand what's going on. So here's one remark. First remark we want to see is that, remember, if you using 3, so 3 is what? 3 is using this result, right? Using this, the variance of this guy is equal to this one. So using this formula, we get this result. So basically, this is the probability. So the pi I corresponding to using the first full model. This is the pi I using the reduced model. But the relationship between so the relationship between, okay, what is the relationship between? So then this is the inverse, right? This is the inverse. So if you compare these two, the inverse, so because so pi ranges between 0 and 1, and then this guy is a convex function. So is it like this between 0 and 1? So right. So then you have a 2 point. Suppose you had 2 point and right. So you can apply Jensen's inequality. So this guy is less than this guy. So you have actually this kind of a relationship. Does that make sense? So what is this, by the way? This guy is expectation of delta equal to 1 of so pi x itself is a conditional expectation of delta given x. And then we take the conditional expectation again on x1. So then we have this, right? So this guy is nothing but this. So my point is that which is what? Which is pi tilde. So if you view it as a weight, this weight is higher than this weight. So, and then this guy is positive, right? So then you are likely, so we can expect that this is usually greater than this one. But it's not really clear how we exactly show this, because we just compare this compare. So in terms of the individual, right? Individual point, we can have this relationship, but yeah.
Well, it's still not individual because you need to take an expectation conditional.
Right. So it's not even right. That's right. You're right. So it's not really, if they are true individually, then we are done, right? But we are more likely. I mean, so this way is not really give the proof. So we need to go another route to prove this theorem, which uses density ratio expression. So first idea is, okay, we can use base theorem formula to obtain this kind of a result. So what is going on here? Well, so so we see marginal. So you can view it as a so here times this one is right. If you so this is a basically joint event, right? The product. The joint event also are the same, but the difference is which one we condition, right? So then this guy is just equal to. So this guy is 1 minus p divided by p, and this is equal to 1. So that we can, and then this guy is 1 over pi, and then this guy is 1 over pi z minus 1. So then you can get, so this formula leads to this expression. And then basically here we view it as a function conditional probability of delta, but here we reverse, right? The flip out and view it as a density, conditional density of z given delta, and then the ratio between the two cases. So that is another way of writing the propensity function, right? Propensity function. And now, okay. And then basically, if you use, so this property is a property of delta given delta equal to 1, delta equal to 1 given z. But z can be anything, right? Z can be anything. So you can put z as x1 and y and apply this formula. Then you get this result. So then where this guy is a joint density of the y1 given delta equal to 0 divided by x1 and y given delta equal to 0, 1. So that's the definition. Okay. So we have two types of formula. One is the using 1 over pi x and y, using full sample. Each one is then r, x, and y, right? So this is the full sample version. This is the reduced sample version. And then let's apply, and then the difference is essentially, so difference between pi and pi tilde is essentially difference between the delta, I mean, r and r tilde. So let's take a look at r function and compute given under this. Then, which is by definition is this one. And then we use, basically this is a conditional distribution. So we can do some, so basically this is, right? You have this is this equal to this. And then what's going on in the why this is true? Well, you can see that what is Rxy? Rxy is the ratio of so Rxy is a ratio of the fxy given delta equal to 0 divided by fx and y given delta equal to 1. Right? So if you multiply Rxy to the density in the denominator, you get numerator. And then you take the integration, integrating out over z x2. Then you end up getting only the marginal. Okay. Then you have cancellation. No, not cancellation. Then you have a R tilde. So that is the lemma 7.1. This one?
No, the first equation.
First equation.
No, the first one. So whatever, yeah.
This one?
Yeah.
So this one, it came from here. So this is the general for any C. Okay. And then I use two choices. One is the full xy. The other one is the reduced to x1 and y. To obtain two versions. So using full one, and this is a reduced one. Okay. So
From the base formula,
I'm sorry.
you're getting this formula from the base formula.
Which formula? Yeah, which
One that
this
I-
one?
Yeah.
So this formula came from here, right? From here to you get this, and then this one basically use leads to this result, or lemma 7.1, and now we are in a position to prove this. So then we have two estimators. One is so let's forget about the denominator. Let's just look at the numerator. And then we have two choices. One is using original full model. The other one is so what am I doing here? What I'm doing here is this is just 1 over pi xi yi. This guy is 1 over pi tilde x1i yi. Right? So then it turns out that because of the lemma 7.1. So lemma 7.1 means what? The full sample density ratio and the relation between full sample density ratio and the reduced model density ratio. And this one is actually a conditional expectation. So basically, this guy and so this guy is a conditional expectation of this guy, which is basically this result. So then this one is a very interesting phenomenon because we have two estimator, but one estimator is a conditional expectation of the other estimator, right? So then which one is better? Laue-Blackwell, right? This is essentially Laue-Blackwell theorem, right? We have whatever it is a conditional expectation should be less variability, right? So that is basically implies this. Okay, and then to finalize the proof, we need to use this conditional pi tilde x1 y is pi tilde x. So we need to use these two properties. because we start with the missing and random, right? So really this R is free of R, and R tilde is actually free of Y, YI. Then you get what we want to show. So this is more rigorous type of proof, but the point is that the point is that the reduced model. So basically, if you can somehow achieve the missing and random with the reduced number of covariate, right? Then it's actually gives a more efficiency gain. So now the remaining question is how to achieve 5. So what is 5? 5 is this one. So how to achieve? So when we get this reduced model, reduced missing and random, and it turns out that we first have original missing and random. So this is original, right? We have original missing and random plus the outcome model is a reduced model. That means X1, X2 is redundant for explaining Y. Then you get reduced missing and random. Okay. This actually, so we are not really making two separate assumptions. Rather, we assume missing and random, and then assume outcome model, reduced outcome model. Then they will imply this reduced missing and random. Okay. So that is the another lemma, and here is the proof. So what we want to prove is the conditional independence between Y and delta given X1. So which is this, right? So Y conditional expectation of Y and delta given X1. So that is the reduced MAR. So we want to show this one from MAR, remember MAR and reduce the outcome model, right? Reduce the model. So let's move on. So, okay. So, yeah. So how to prove it? Well, you can basically you consider joint density and then integrate out over unnecessary things, right? So here's you have a marginal density of X and then X2 given X1 and delta given X and Y given X and delta. That means what? Full joint, right? You have a full joint, and then to make this one, you need to get rid of X2, right? So you basically integrate out over X2. So that's what we did in the numerator. In the denominator, it's the same thing, but the denominator, we also need to get rid of Y. So that's why we have integration over Y, right? In the denominator. So at least the first equation is just a kind of definition, right? I mean, nothing really new. And then from here to what about second? So let's take a look at what's the main difference. Well, okay. So two things actually. So first thing is we need to cancel out. So why? Because of MAR, original MAR, right? We have an original MAR, so then this Y given X and delta is equal to Y given X. So that's original MAR. And then reduced model assumption. So reduced model assumption is Y given X is equal to Y given X1, right? That is a reduced model. So that is actually used here. So that we have a X now change it to X1. Right? So with delta cancels. Delta disappears and then X1 is to X1. That's the main thing. Okay. And then once you make this one function of X1, then it's free of x2. So you can move this one outside the integration. Okay, so this guy can go outside the integration.
So in the second line, why it is inside the integration?
Huh?
It should be outside the integration.
Which one?
The second line.
Second line what?
A function of y given x1.
Okay,
Because you integrated out in terms with respect to x2, right?
x2, right?
So it should be outside the
Yeah.
integration.
So this goes outside here.
Okay, in this, I am talking about the second line.
So okay. Yeah, so this is basically this is definition, right? Definition. This one uses this one and MAR, right? So this one we use MAR first to get rid of the delta, and then reduce the model assumption to get this one. And then this one is just moving this one outside the integration. So then you have basically this one, so diffusion, and then basically then this guy is a definition of the right. It's basically simple. So what is this one? This one is you're taking, yeah. So pi tilde essentially. And then cancels actually. So the point is that, so okay, be careful. Okay, so yeah, this guy is equal to, both of them are equal to pi tilde x1. And then this guy has nothing to do with the y, so it's just cancels to each other. So and then you take the integration of y, which is equal to 1.
Do I have a question?
Yeah.
If you go to the previous page. Yeah, so, right, this is the lemma. Right, so if we find the minimum set that satisfies this, so that one should be, has a smallest variance, right? So can we show that this is optimal?
Well, we don't probably not. Well, what do you mean by we don't have an estimator?
Well, you have the estimator, like you said, right?
Yeah.
You have the inverse probability weighted estimator.
So
You just weight probability for.
So weighted estimator is never optimal because you are basically ignoring the partial information in X, observed X.
Right.
So that is just the beginning, and then next class will cover some optimal estimation.
Okay, so we still need to do the response
Right.
model. Sorry, the outcome model.
Yeah, right. So this one only uses the response model
Right.
at this point. Yeah. Okay, so that basically take care of the first section, and I have about 10 minutes, and I have about 7 pages slide. So I think we should be in good shape. So okay, about regression weighting we already covered, so it's kind of reviewing what I covered before. So the regression weighting technique. So well, the motivation is this. So we are pi I, so we know that this is the propensity, right? So to compute the WCC, whatever, or PS estimator, we need to know pi I and then apply as a weight 1 over pi I, something like that. So that is the motivation. And so modeling pi I is somewhat difficult, right? How to model, how to make a model submission. So this is actually original Fuller's idea. So Fuller's idea is that there what would be the robust way of weighting, non-response weighting without explicit modeling of the pi I. So that is the so this is kind of indirect way of propensity weighting. So his idea is use this regression weight and see under what conditions it is unbiased. So basically this is the weight. You have a delta x always observed. You have an intercept here, and y is a study variable, which is observed only delta equal to 1, and then this is the regression weighting. So remember, what is the nice thing about this one? Remember, if you use this one, right? If you use this one, then you can write it essentially as of x prime beta hat 2, beta hat r, or so beta hat responses. So where beta hat is right? So this is basically regression coefficient using delta equal to 1, and then you just have a regression imputation, right? This is just nothing but you just predict everybody in the sample using regression code, right? Prediction. And then once you predict, you view it as a function, linear function of y, and then use this weight as the final weight. So that is the regression weighting. And so the big question is also that this is basically this one already. So big question is under what conditions the regression weighting method is justified under the response model. So one assumption, right? So previously, this regression estimator is justified under the outcome model, regression outcome model. So, right, under this model, this regression estimator justified. So there's one assumption that justified one sufficient condition, but that is not the only way. So that's not only assumption that justify this estimate. So another assumption. So this is one, and second assumption. So basically we wanna say that either this assumption is true or another assumption is true. This is unbiased, right? And what is the another one? That is next page. So that is this. So if the response mechanism, true response probability, inverse of the true response probability is in the column space of the X, then this. So this assumption is an assumption about. So this is the assumption about the pi I, right? Pi I is the, remember, pi I is the delta equal to 1 given xi. So this is actually a model assumption about delta response mechanism. And then under that assumption, so this is basically second set of assumption that justifies the regression estimator. Okay. And so here's a justification. So first one to note is that let's consider no missing. Then this is the unbiased estimator, right? Y sample mean. And then also because we have a intercept is here, we have a basically it will be 0, right? So the residual will be property of the residual sum to 0, right? So that means this guy is equal to this guy, which is basically this. Okay. So then you can write the difference between the regression estimator and the sample mean as this. And then now we need to evaluate the conditional expectation of the difference. So we want this conditional expectation to be 0, right? We want conditional expectation to be 0. And then, so basically, so now, so we have only to show. So we want this to be 0. That means we have only to show that this is 0. Which is this one. But we already know that this is 0, right? We already know that this is 0. So that means if you can write this way, right? This is what? This is the assumption, right? Assumption 10. So assumption is pi I inverse is lambda prime xi. So in that assumption, we can write this way. And then lambda can go outside. And so that means lambda is not 0. So this is 0, right? Because this is 0. So, okay. My point is lambda can go outside, and then the remaining term is just this one, right? But this is 0. So that means because we know that lambda is not 0, that means this is 0. Okay. Well, yeah, and then that gives the justification, and then the linearization. This linearization formula is actually exactly what I already described before. So just skip. So that's for regression rating, and I will. So again, I will not have a class this Thursday, but I will have a recorded lecture, and sometime this Thursday, or early Friday, something like that. Okay.